Hello, here we continue by finding the diffusion coefficient using the value of diffusion coefficient at a certain temperature, as you can see here. In this example, the diffusion coefficient at 300 degrees Celsius is given. We know this is for copper in silicium. The activation energy is given, as you can see here, and the value of diffusion coefficient is shown here. We want to find the diffusion coefficient at 350 degrees Celsius. Now it's clear that based on this relation there is an exponential relation between the value of T and temperature. So we can have this curve, or this orange curve between L and the logarithmic value of d2 logarithmic value of d and reciprocal of temperature in degree Kelvin. If we use the same relation and we divide them, this relation for temperature T1, which is 300 degrees Celsius or 573 degree Kelvin, and use it to know the value of d1, and then we have d2 at t2, and then we divide them together, then the value of d0 will be cancelled, and we end up to a relation like this, in which the value of d1 is known, the value of qd, or activation energy, and constant of r, t2 and t1 are known, so we can easily find the value of d2 at 350 degrees Celsius. If you work out this problem, you will see that the value of dt is about 15.7 times 10 to minus 11 meters squared per second. If you have access to MSE, you can find and generate plots of logarithmic value of d versus 1 over t for different types of diffusing species into host metals, as shown here. In the non-steady state diffusion, unlike to steady state diffusion, the concentration of diffusing species is a function of both time and position. So we can write down the concentration C is a function of x, position, and time, as you can see here in this graph. In this case, fixed second law is used, which is shown here, which shows the dependency of concentration on time and position. Here, copper diffuses into a bar of aluminium, as shown schematically. The surface concentration, which is shown by Cs of Cu atom, is shown here in this graph, and you see there is a pre-existing value of concentration, which we know as C0. Here, for all value of x from 0 to infinity, the value of C is equal to C0 at t equal to 0. The first or the pre-existing value of concentration is the same for all value of x, so we can write down at t equal to 0, C is equal to C0 for the whole value of x from 0 to infinity. At t, by increasing the value of t, so t bigger than 0, C is equal to surface concentration, or Cs, for x equal to 0. As you can see, it starts from this one, and then this value decreases, and of course it depends on time. In other words, the value of surface concentration is constant at x equal to 0, and of course for x equal to infinity, disregard to the time, the value of C is again equal to pre-existing concentration. So these are the boundary conditions that can be used for the solution of non-steady state diffusion. Okay, if we write down the boundary condition as we talked in this format, and then we use it to solve this differential equation, we end up to this relation between concentration value at point X and time t, and the other values that are known C. In this relation, C0 is pre-existing concentration, CS is surface concentration, and this is an error function of this value. X is the position, D is diffusion, and T is time. As you can see in this relation, the value of error function, how we can find it if we plug the value of Z instead of all these fraction, then we can find the error function of Z using this relation here. The value of error functions or different values of error functions for Z starting from 0 to 2.8 are given in table 7.1, page 187. This is also given in this table. As you can see, concentration at position X time t is a function of pre-existing concentration, surface concentration, of course time t, the position of X, and diffusion based on this relation. Bear in mind that this is the solution to fix second law for the condition of constant surface concentration, and of course for a semi-infinite solid. Now let's solve a sample problem regarding non-steady state diffusion and the equation that we just talked about, the solution to the second fixed equation. Here in FCC ion carbon initially containing 0.2 weight per carbon is carburized at an elevated temperature. So here 0.2 weight percent of course is the initial value, or the value that we know as C0, or the pre-existing concentration. And it says the surface carbon concentration constant at 1 weight percent, so the value of CS, or surface concentration, is 1. If after 49.5 hours, the concentration of carbon is 0.35 weight percent, so 0.35 weight percent here is the concentration at point X and or position X, in which position X is equal, or X is equal to 4 millimeter. It says a position 4 millimeter below the surface. Of course the value of this is the total value of time. It's 49.5 hours. Now we want to determine the temperature at which the treatment was carried out. So the first step is we have to gather the known information, and of course we have to use equation 7.5 shown here. 49.5 hours, the concentration of carbon is 0.35 weight percent, so 0.35 weight percent here is the concentration at point X and or position X, in which position X is equal, or X is equal to 4 millimeter. It says a position 4 millimeter below the surface. Of course the value of this is the total value of time. It's 49.5 hours. Now we want to determine the temperature at which the treatment was carried out. So the first step is we have to gather the known information, and of course we have to use equation 7.5, which is this equation shown here. I have entered here the known information: time, concentration at position X, initial or pre-existing concentration. The value of X is known because it's 4 millimeter as shown here, and the final value is surface concentration, which is equal to 1 weight percent. So if we use these values and plug them into this relation, we can find the value of error function. The value of error function from this known value is 0.8125. So now if we go to table 7.1, by having this value for error function, let me just enter the value here. So error function f is equal to 0.8125. Now we go to table 7.1. If you look at table 7.1, you see this value for error function z is between, it is in the second column of the table, and it is between these two values, between values 0.797 and 0.8209. Of course, the value of z gonna be between 0.9 and 0.95. So by interpolation we can find the value of z, and we know that z is equal to this value, x divided by 2 root of dt. We know the value of x, which is 4 millimeter. We know the value of t, which is 49.5 hours. By knowing this, we know the value of d. Now we go and use the other relation, which is showing the value of diffusion based on temperature independent pre-exponential, equation 7.8. If we want to use equation 7.8, and of course we have to know the value of d0 for carbon into FCC, because if we go back to this question, it's talking about diffusion of carbon into FCC ion. So we go to table 7.2, which talks about diffusion data, and you see the second row is talking about diffusion of C into Fe with gamma phase or FCC. The value of D0 and activation energy can be found from here. D0 is 2.3 and activation energy is 148,000 joules per mole. So if you plug QD and D0 into equation 7.8, of course we know the gas constant. Then from here, by knowing the value of D, we can find the absolute temperature, which is equal to 1300 degree Kelvin, and we can convert it to degrees Celsius. We can work this in the class.